All right, guys, here we go, section 4.4. We are now getting into basically some shortcuts into proving that triangles are congruent. So we saw in section 3 that in order to prove that two triangles are congruent, we had to show that all 6 of their corresponding parts were congruent. We had to show that all 3 sides and all 3 angles were congruent in order to say that the triangles are congruent. But what we're going to see in the next couple sections are some of the shortcuts that we can use in proving that two triangles are congruent. So in particular, in section 4, we are going to see that the side-side-side postulate is one of the shortcuts, as well as the side-angle side is one of the shortcuts. So here's the idea. Instead of showing that all 6 corresponding parts are congruent, we can simply come up with just this information or just this information, and that's enough. That's enough to say that the triangles are congruent. Basically what we're seeing is, if I can show something like all 3 sides of one triangle are congruent to all 3 sides of another, then automatically, and we'll have other rules for this, but automatically all the angles are going to have to match too, right? And so if that's the case, then we're going to be able to come up with all 6 corresponding parts. So let's just start out with the first one. So side-side-side. And again, if you're taking your own notes, if you don't have this printed and you're writing down your own, you do need to copy down this side-side-side postulate, as well as the proof that we're going to go through right here. All right, so for side-side-side, if we can come up with showing that all 3 sides of one triangle are congruent to the 3 sides of another triangle, that's going to be enough to say the two triangles are congruent by side-side-side. So let's just take a look at what they laid out first within this proof. So of course they started out with a given, and we just threw out the given information. And one thing that is so important on this, especially over these next couple sections, is marking the diagram with the statements that are made in this proof. And that is going to be giant when it comes to coming up with this final statement down here. We're gonna need to show within our diagram where that came from, because once we learn more of these, like side angle side, angle side, hypotenuse leg, like there's a handful of these that we're going to be learning, and the best way to tell which postulate or theorem supports your reasoning is by the markings on your diagram. So that's going to be a really big thing to do as we go through. One of the things you will hear me say on this a couple times is, don't mark your diagram until you've said it within your proof, right? Because that's important. A lot of times students will see things like, oh, I have a reflexive line, or whatever the case is, and they start marking their diagram, but they never actually said it in their proof. And so we do need to make sure that whatever gets marked on here is said within our proof. So they started out with our given, and they marked the given information that AB is congruent to DB, so you can see by those double marks right there that that's what was marked. And so where do we go from there? So from there, let's take a look at what we can use from our given information. Now they told us in the given that point C was the midpoint of segment AD. Right? That was given information. So point C is in the middle of AD right here. So what does that tell us? Well, that must mean that AC is congruent to DC. So now that we've said it in our proof, we're going to go ahead and mark it. So AC is congruent to DC, and our reason for that, and this is something we talked about a while ago. Now they're saying it's the midpoint theorem. Now we've had some discussion on this. We looked at the midpoint theorem can be a little bit limited in its use, right? And so the other thing that we've talked about that went back to chapter 1 was the definition of midpoint. Because the definition of midpoint is a little broader than the midpoint theorem. The definition of midpoint says that segments are congruent and equal. So the definition works for an equation or a congruent statement, whereas the midpoint theorem only works for congruent statements. So here's what I'm trying to get at here is, this is a valid reason, but you could have also said definition of midpoint. And if you're ever in doubt, I would use the definition of midpoint because it works for more cases than what the midpoint theorem works for. So anyway, so we do know by definition a midpoint that those two segments are congruent. And then here's something we've also talked about this chapter, is these triangles share a common side. BC belongs to the left triangle, BC belongs to the right triangle. Obviously BC is congruent to itself. So whenever they share a common side, we always want to recognize that reflexive property that says something is congruent to itself. Therefore we can use it in our proof. So now look at our diagram. You'll notice that we have marked that the three sides of the left triangle are congruent to the three sides of the right triangle. And since those guys have been marked, we can go ahead and say that the two triangles are congruent by side, side, side. Guys, when it comes time to filling in your own congruent statement, like this one, something that we talked real big on in the last lesson was make sure that the order of these letters do match the order of these letters. Right, so this was already identified right here, so we're fine with this congruent statement. But do notice that ABC, so ABC, does correspond to triangle DBC. In other words, angle A corresponds to angle D. Angle B corresponds to itself, of course, and angle C corresponds to itself, of course. So the order did line up from one triangle to the next. You can switch this order, but these have to be switched as well in order to match it. But that's not something we're worried about when it's already been identified for us like this one has in this proof. So let's jump on down to writing our own proof. And this will be real simple. So here's one where you could even sort of pause and try on your own if you want before I do it. But again, if you're taking notes on your own, make sure that you copy this example down. So as I look at this one, of course, within my statements and reasons, I'm going to start with my given information, which said that RS is congruent to UT. And you'll notice on this one, they've already marked that for me right here and right here within my diagram. And if they didn't, of course, I would do that. We also were told that RT is congruent to US. And all that was given information. And all that's been marked already, so we're good to go. So beyond that, there's always two things we're looking for. Is can I use the given information to say something more, or can I use my diagram to say something more? The given has been exhausted. There's nothing more I can get out of that given information. So let's go to the diagram, and what do we see? So here's that reflexive property coming up again. TS, of course, is congruent to itself. So we're going to say that TS is congruent to TS. That's our reflexive property. And now by the markings, we can see that we've covered enough information to say that the two triangles are congruent by side, side, side. Right? So I got a side, side, side matching up with side, side, side. So, and this is the easiest of the group in order to use as far as like the shortcuts are concerned. But so let's just write our final statement. The triangle RST is congruent to triangle UTS by side, side, side. All right. So let's move on to the other shortcut of the day, and that is our side angle side postulate. Side, angle, side. Again, guys, if you're taking your own notes, please copy down what you see in this box, as well as the examples that you're seeing on this page. You need to copy these down as well. Let me try to refocus that, make sure this is nice and clear for you guys. So one of the things that we do within this second half of this chapter is we're going to start looking for which postulate or theorem is available, like side, angle, side, 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 side. We're going to get to some more like angle, angle, side. But anyway, instead of doing the full-blown two-column proofs every single time, sometimes we do what I would maybe call sort of a mini proof, which is we're using valid reasons to mark these diagrams and to say what we see within the diagrams without actually writing out the full two-column proof. So we're only going to do the 2-column proofs when the directions specifically say. But there's going to be other times like these ones where it's just kind of looking at them on our own and determining whether we not have enough information to prove that the triangles are congruent. So if you look at A, the first one, do we have enough information? So here's one of the challenges with side angle side. And this is huge, so make sure you hear me on this. The order that you see these letters matter. Okay, so the way that we want to read this is when we say side angle side, what we need to see is the angle between the two sides has been marked. So in other words, as I look at this diagram, I see a side, and I see an angle. But is that side angle side? Is the angle that's been marked the angle between the two sides that's been marked? Right? We call that the included angle. Right? The included angle is the angle between the two S's that we've marked. Well, we mark this side and this side, but where's the included angle? Right? If I look at those two sides, angle A would be the included angle. And I would need to know angle A is congruent to angle X in order for me to have side angle side. So again, when you say side angle side, the angle that we're referring to has to be the angle between the two sides that you marked, like this one is. Right? So there they mark the included angle. This one is not the included angle, so therefore this is not side angle side. Take a look at this one though. Here's the difference. Now I do know the angle between the two sides that we marked on both triangles. So now I do have a side angle side scenario. There is a little more information on this one that we would need to identify. Like for example, if you look at angle F and angle H, they didn't mark them as congruent. They marked them as right angles. They marked them as right angles. But if we were doing a proof, knowing that angle F and angle H are right angles, would we be able to prove that those two angles are congruent? Right? And of course we have the right angles congruence theorem, which says that all right angles are congruent. Right? And so even though they didn't say angle F and angle H are congruent, if we were doing a proof, we know that we could come up with that information because we have reasons to back that up. Right? We have the right angles congruence theorem, which says that all right angles are congruent. So if we were doing a proof, we know that we'd be able to say that this angle is congruent to this angle by the right angles theorem. Therefore, I do have side angle side information. Right? But again, the important thing I really want you guys to get out of this discussion is the angle that we're referring to is the included angle. Right? It's the angle between the two sides that has been marked. Let's look at one more here. Taking us back to chapter 3 and those parallel lines that we've been talking about this chapter. So as I look at C, I can already see that a couple of the sides have been marked for us. And one of them, the one in the middle, we would have been able to do on our own. They marked it for us. That was given information, but they really didn't have to. That's that reflexive line, right? PR is of course congruent to itself. So we could have marked it if they didn't. And that's one of the biggies that will come up a lot in these next couple sections. So as I look at this, what more could we say? Well, as I look at parallel lines, again, I want to think back to chapter 3, where I have parallel lines cut by a transversal. So here's a miniature version of what we saw in chapter 3 that looked more like this. Right? That was more of the drawing, but really it's the same information that I'm seeing, right? If this line is parallel to this line, so if you look at angle 1, which is here, and if you look at angle 2, which is here, right, we learned in chapter 3 that those are alternate interior angles, and by the alternate interior angles theorem, since these lines are parallel, those guys have to be congruent to each other. So if we were doing a proof, we would be able to look at this and say, yeah, angle 1 is congruent to angle 2 because they're alternate interior angles. And now by doing that, I do now have side angle side. All right, let's try some on our own here. One of the reasons I really like those problems that we just looked at and I'm going to zoom in a little so you can make sure you can see this nice and clear, is if I'm going to do a full proof, I kind of like to go through that information on my own before I even go through the proof, is I want to kind of do an overview of this and say, what am I going to be able to come up with here? So like right off the bat, I'm seeing, hey, there's the reflexive line, that PL is congruent to PL. So I know I'm going to be able to use that in my proof. And with perpendicular lines, I'm going to be able to use that in my proof too, and say that right angles are congruent. So I'm already seeing some things I'll be able to use in my proof. And I'm trying to refocus here a little bit for you. I'm kind of moving it towards the light in and out here because it looks like it's a little unclear. But we'll do our best. And if you have these printed, you'll be able to see this anyway. So here we go. So we got our statements and reasons. So on this one, let's just start out with our given information. NP is equal to PM and NP is perpendicular to PL. And that, of course, is our given information. So we're always going to start there. One thing that disappointed me a little bit in this proof is the way it was introduced. You'll see these markings in our diagram, but we have not yet said that within our proof. So that's one thing you have to be extremely careful about. We have not said that NP is congruent to MP. We said that they were equal, right? So we still need to say that they are congruent. We haven't said that yet. So these should not have been marked in advance, as well as the right angles, right? Well, what they said is we have perpendicular lines, but they have not said that we have right angles. So those things need to get said within our proof. So as I look at what I'm going to say next on this, let's look at our given information and see what more we can pull out of this. So NP, because these guys are equal, we also know that NP is congruent to PM by definition of congruence. Or we could say, and the book says, definition of congruent segments. So we could say either one. I'm okay with the shortcut of saying definition of congruence. The book would say definition of congruent segments. But in any case, we need to say that the lines are congruent, not just equal. So that's a step that we needed to take, and now we could mark it within our diagram in those two places. I'm also looking at this, and if you look at the bottom of page 48 in our textbook, the bottom of page 48 says that the definition of perpendicular lines says that they create 4 right angles, right? And so I can use the definition of perpendicular lines to say that angle NPL is a right angle, and angle MPL is a right angle. And that is the definition of perpendicular lines. And so really important that those things get said within our proof. We can't just start marking things on assumptions and saying, well, I know what I would say in the proof. This is actually the full proof, right, where they really want to see all the statements laid out. So now that we know that these two guys are right angles, we can use the right angles theorem to say that they are congruent to each other. As I look at this chart on the bottom of page 155, again, here's the theorem that we can now look at. There was a theorem that came up in chapter 2 that said that all right angles are congruent. So do keep in mind that when you're seeing stuff like this, there's 2 ways to write a reason, right, in the reason column. One way is to just write what the reason says, or what the theorem says. The other way is to name the theorem. So I can now say that angle NPL is congruent to angle MPL by naming the theorem, which is my right angles theorem. Or I can write out what the theorem says, which is that all right angles are congruent. And so you could do it either way, right? We can give it sort of the official name, or we can write out what the theorem says. And you can do that with all these. It's just usually quicker to write the name rather than the entire definition or the entire theorem, stuff like that. So that's why it's usually easier just to name it. But you could write out the full reason, and sometimes our book does that. But anyway, let's take a look at what we got so far in this proof. So as I look at this, now I can say that this angle is congruent to this angle because we just set it within our proof. I do need one more piece of information, and here comes that reflexive line that you guys are going to see again and again and again, so you're going to get used to this one. But of course, PL is congruent to itself. By the reflexive property. And now if I mark that on my diagram, now look at the markings, right? Now if I look at either one of those triangles, I can see that I've marked two sides and the included angle on both triangles. Two sides and the included angle. Therefore, I can now say that triangle NPL is congruent to, and that reason is our new one. That is our side angle side. Shortcut, right? Postulate. But anyway, one of the things that's kind of neat to do within these proofs, do in the past, is when you say stuff like this, sort of highlight that. So let me grab a different color so I can make this stand out a little bit. Let me do this one in red. So right here I said I named a side with a congruent statement. Right here we identified congruent angles. And then right here, again, I identified a congruent side. And so now I can see, yet for sure, within my proof, I have come up with enough information to use this postulate to finish it off. So let's try this one as well. Write a two-column proof. So I'm going to go through this one a little quicker. So as I look at this one, guys, one of the things you're going to see on these is a lot of the same reasons keep coming up. And that's why I want to keep doing these proofs, is you can see like I said, the reflexive line, those types of things are just going to keep coming up. They use a lot of the same reasons within these proofs, right? And so it's good to start recognizing reasons like this. So let's just look at a plan of attack here. Obviously they're saying AB is equal to CD, which again, I don't like those marks in advance. We haven't said they're congruent yet. That's going to need to happen within our proof. They've also told us we have parallel lines. Now that's huge because that has to stand out to you from chapter 3, is to be looking for things like alternate interior angles as soon as I see parallel lines. So let's just start out with the given. AB is equal to CD. And AB is parallel to CD. Of course, that's given information. All right, so let's move on to the next line. So guys, again, if they're going to say that AB is equal to CD, we really should take the step of saying that AB is congruent to CD, which is the definition of congruence. Or you could say definition of congruent segments if you want to extend that out, but again, you don't have to. So now I would mark it on my diagram. All right, so guys, the reason I'm doing that, just so you know, is if you look back at what the postulate says, I'm just going by this definition, right? It says that the two sides and the included angle are, here's your key word, are congruent. It doesn't say they're equal. It says they're congruent. So that's why I'm taking that extra step of identifying congruent parts, not equal parts. So what more can we get from our given information? Well, this one's sort of a combination of the given information as well as looking at the diagram. But as I look at this, if AB is parallel to CD, that's going to make alternate interior angles congruent. So let's call this angle BAD. Is congruent to triangle CDA, angle CDA. And again, all leading back to this idea right here. Those guys are alternate interior angles theorem. That's our alternate interior angles theorem. Notice again, once I've set it here, I then mark it in my diagram. So we have now come up with a side, an angle. So you can see that's not quite enough information. What else can we say? So here's that super popular reflexive line again coming up, that AD is congruent to itself because it belongs to both triangles. So AD is congruent to AD. That's our reflexive property. So here is that information right there, and now clearly I can see within my proof and in my diagram that I have come up with the side angle side theorem. Therefore, triangle ACD is congruent to triangle CAB by SAS. All right, let's keep it going here. I do have one more thing to show you. How do I know in a coordinate plane if two triangles are congruent? So let's just plot these points real quick. So point A is negative 3, 3. So at A, I got B is negative 1, 3. And C is negative 3, 1. So here's my triangle. I'm trying to make it stand out from the rest of the lines there to make it a little squiggly. So that was A, B, and C. And let's do KLM. So K is 1, 4. L is 3, 4. M is 1, 6. So that was KLM. All right. So guys, just so you know, as always, there's more than one way to do this, right? And so that's something I've been kind of preaching all year long, is there can be certainly more than one approach. Okay, so let me just give you a couple ideas. I'm still thinking of the same ideas that we just used. So I can come up with side, side, side. I can come up with side, angle, side. There's multiple things I can come up with right now. Let's just talk about side, side, side for a minute. How can I tell that these three lengths are congruent to these three lengths? Right. Well, a couple things. I can count these guys. Right. From A to C is 2 units. From A to B is 2 units. I can count those. I can also count these here. 2 units and 2 units. So if it is a vertical or horizontal line, really easy to just count. So that's 2, that's 2, that's 2. So I can tell just by counting that I have congruent sides, right? And I'm not doing a full-blown proof right now. We're just trying to determine if these triangles are congruent. So I can count to show that those 2 legs of each triangle match up for sure in length. If I want to use side, 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 well, how do I come up with a third side? I cannot count if it is at an angle, right? You cannot count the length of a segment if it's traveling at an angle like this. So how would I do it? Well, we could use our distance formula. This goes all the way back to the beginning of the year. Is I can use my distance formula to show that CB is equal to ML, right? And that's one approach. What would be another approach? How could I use side, angle, side? Well, if you look at these triangles, I can see that AB has a slope of undefined. AB has a slope of 0, right? And so as I look at these, I could show that those 2 lines are perpendicular, therefore they form right angles, therefore right angles are congruent, and I could come up with SAS. We could certainly do that using slope. What I've seen in the past is students have a harder time with that. They have a harder time showing the proper steps using slope. So you could certainly do that, and there's nothing wrong with that. But I'm going to go with the one that people have a little more success with, which is the distance formula. So I'm going to do my distance formula for CB. And that takes you all the way back to some earlier stuff in the year. Remember, distance is length. So if I can show that the distance from CB is equal to the distance to ML, that's also saying that their lengths are equal, right? Distance is length. So Distance formula was the difference in your x's squared plus the difference in your y's squared under that radical. So that's our distance formula. So let's look at CB. So I'm going to start with the difference in my x's. -3 minus -1. Difference in my y's, which would be 1 minus 3. So right here, -3 plus 1 would be -2. Squared would be 4. Right here, -2 squared would also be 4. So I'm looking at the square root of 8 for the length of BC. So let's do the same thing with ML and see if we get the same information here. So again, I'm going to have my difference in my x's. So I'm going to do 3 minus 1 squared plus the difference in my y's, which would be 4 minus 6 squared. So again, this would be 2 squared, which is 4. This would be -2 squared, which is still 4. And so you'll notice ML is also, that ML gave me the same result as BC. So I have shown that the third sides are congruent. This guy is the square root of 8, and this guy is the square root of 8. So now I have enough information to say for sure, yep, those two triangles are congruent because of side, side, side.